Welcome to the Deep Dive. Today we're plunging into this fascinating world where cutting-edge code meets real-world business needs. And look, for anyone truly looking to leverage artificial intelligence, there's this fundamental challenge, really, that often separates the builders from the true problem solvers.
Yeah, that's what we often call the two-language problem in AI. It's this core idea that the most impactful AI professionals, well, they're genuinely bilingual.
Uh-huh.
They don't just speak the technical language, Python, TensorFlow, algorithms.
All that stuff.
Right. Crucially, they also speak the business language, return on investment, KPIs, customer lifetime value, that side of things.
And it's such a critical distinction, isn't it? Because a technically perfect model, one that's brilliant in its code and execution, it's actually a failure if it doesn't address a core business need.
Totally.
It's like building this incredibly sophisticated machine that, solves the wrong problem altogether.
Precisely. And our mission today, really, is to provide a kind of career blueprint for you. Maybe you're a technically proficient developer or an aspiring machine learning engineer ready to bridge this exact gap.
We're going to unpack the multifaceted skill set required to transform all that amazing code you write into genuine customer value. You can expect us to navigate the entire production-level project lifecycle, from translating, vague business objectives into solvable ML problems, to assembling and collaborating within a modern AI team, building, deploying, maintaining production-grade systems, and finally, how you can cultivate this indispensable skill set. So let's kick off with what many of our sources identify as the most crucial stage, and often the most failure-prone too, the art of translating business needs into machine learning problems.
It's absolutely fascinating because when you look at some of those high-profile AI project failures, like IBM's Watson for Oncology, or maybe Zillow's iBuying algorithm, they didn't typically stem from technical incompetence. The models themselves were often incredibly sophisticated. The issue was a fundamental misalignment. They built a perfect model, sure, but it solved the wrong problem, which in a business context often delivers negative value, frankly.
So the core skill here isn't necessarily just coding the fanciest thing. It's asking why. You start with a vague request. Say, we need an AI to improve efficiency. Okay, well, that's not a specification, is it? It's just the very beginning of a conversation with your business stakeholders. You have to dig deeper, right?
Exactly. You absolutely need to ask those follow-up questions. Efficiency of which specific process? How is this efficiency measured today? What's the target improvement in that metric? And maybe most importantly, what specific decision or action will this AI system actually inform or automate? Without those answers, you're just guessing.
Yeah, the IBM Watson for Oncology case study really underlines this misalignment you mentioned. The ambition was huge, revolutionary even, recommend cancer treatments using AI. But the ML problem, it was framed too narrowly, wasn't it? Based on data heavily influenced by just one institution, Memorial Sloan Kettering. What was the impact of that?
Well, it meant that Watson's recommendations, while technically derived from the data it saw, were often impractical or inconsistent with local practices, drug availability, standards of care, and other global settings. The model was sophisticated, yes, but it solved a version of the problem that just didn't fit the real-world diverse context where it was being deployed. It really highlights that context is king.
Which brings us to a key distinction that needs to be crystal clear for anyone working in this space. Business KPIs versus model metrics. Business KPIs are your ultimate targets, things like revenue lift, customer lifetime value, reduced operational costs, maybe improved delivery times. These are the goals that the business really cares about. Model metrics, on the other hand, they're the technical measures you use during development: accuracy, precision, recall, RMSE, things like that.
And the real art is to ensure your chosen model metric serves as the best possible proxy for your business KPI. It's not always straightforward. Imagine a logistics company. Their KPI is percentage of on-time deliveries. Okay. So optimizing their model for shortest total distance might seem logical at first glance.
Yeah, seems reasonable.
But in the real world, this could totally ignore crucial factors like traffic congestion or specific delivery windows the customer requested. The model could technically find the shortest path, sure, but still fail miserably at improving on-time deliveries. It's technically right, but practically wrong for the business goal.
And sometimes the true business outcome isn't directly measurable at all, right? Like, how do you quantify if a user actually enjoyed a recommended video or article? It's subjective.
Exactly. That's where these proxy labels come in. YouTube, for instance, might use something like watch time or did the user hit the like button as proxies for user satisfaction. Choosing the right proxy is a really critical decision. It requires deep domain understanding and, honestly, often some creativity.
Okay, so once that problem is crystal clear, you then need to choose the right ML paradigm, the right tool for the job. If you're asking which category does this belong to, you're probably looking at classification, right? Things like spam detection, fraud analysis, sentiment, customer return, prediction.
That's right. And if the question is more like how much or how many, then regression is typically your weapon of choice. Predicting things like house prices, inventory levels, maybe customer lifetime value in dollars or delivery times in minutes. These are often about making a single kind of static prediction.
Now, if classification and regression give us those static answers, what about problems where the answer needs to keep changing based on a sequence of decisions? That, to me, is where the true dynamic power of AI shines through with reinforcement learning, or RL. This is for when you need a system to make a sequence of decisions in a dynamic environment to achieve some long-term goal. Think optimal pricing that changes with demand, real-time ad bidding, complex inventory management, or even, as you mentioned, how Google cooled its data centers more efficiently.
Yeah, it's about learning from the consequences of actions over time, not just making one-off static predictions based on past data.
Yeah.
It's a different beast altogether.
Before you leap to any of these, especially the more complex ones like RL, there's this crucial rule-based litmus test we should talk about.
Absolutely essential. Always ask yourself, could this be solved effectively with a simpler non-ML approach? Like maybe just a few if-then statements. Our sources recount this story of a major retailer. They spent 8 months, significant resources, building an ML model for restocking products,
Okay.
only to find out that a simple rule, something like if inventory is less than 10% of average monthly sales reorder, actually performed better and was far, far easier to maintain.
Wow. That's a great point about not over-engineering. Just because you can use ML doesn't mean you should.
Exactly. The goal is effective and efficient problem solving, not using ML for its own sake or because it's trendy.
But I wonder, what about situations where a simple rule seems to work okay, but you might be leaving a lot of value on the table? Like you're missing incredibly subtle patterns that only ML could uncover, and that's costing you future opportunities. Is there a risk of being too conservative with that litmus test?
That's a fantastic question, and it really hits on the balancing act here. The litmus test isn't meant to avoid ML at all costs. It's about justifying it properly. If a simple rule gets you, say, 80% of the way there with only 10% of the effort, that's usually a massive win, especially early on. Start there. Then the next step is to critically analyze if that additional 20% of value that ML might unlock is genuinely worth the extra 90% of effort, the complexity, the ongoing maintenance burden. It's about being pragmatic, making smart trade-offs, not just defaulting to the most complex solution.
That makes a lot of sense. Pragmatism over complexity. So once we understand the why behind the problem and we've chosen the right approach, maybe it is ML, maybe it's a simple rule. How do we actually build the solution in the real world? That's where the modern AI team comes in, right? This idea of collaboration with cross-functional teams isn't just corporate jargon anymore. It feels like the fundamental operating model now.
Oh, absolutely. An ML engineer isn't a lone coder hiding in a corner. They're really a central node in a highly collaborative network. Project success absolutely hinges on communication and seamless integration across different roles.
And the ML engineer specifically often acts as this sort of production linchpin, wouldn't you say? Sitting right at that intersection of data science, software engineering, and operations, or MLOps.
That's a great way to put it. Their role involves everything from re-engineering prototypes, often born in notebooks, into robust, production-ready code, to building automated model pipelines, managing the computational infrastructure needed, and then deploying and integrating these scalable models into the actual business processes or products.
Okay, let's quickly walk through some key roles in this cross-functional team and how you, if you're the ML engineer, typically interact with them. First up, the product manager, the PM. They define the what and why. They own the business objectives. What's that relationship like?
Well, they need realistic feasibility assessments from you. Can this actually be done with AI? And clear explanations of what the model can and can't do. And you, in turn, you absolutely need from them a clear definition of the business problem and those specific measurable KPIs we talked about earlier. This upfront alignment is just critical to avoid going down the wrong path.
Then there's the data scientist. They're often the ones exploring the data, developing the initial prototypes, maybe in Python notebooks or R. How does that dynamic work with the ML engineer?
It's usually a close partnership. They need your help with implementing production quality code practices, figuring out how to scale their prototypes, and getting access to the right infrastructure. You, on the other hand, need their documented prototypes. You need to understand the logic behind the features they engineered, and you need their experiment metrics to guide your productionizing efforts. It's about taking their research and making it robust and scalable.
Got it. And the data engineer. They're building the very backbone, right? The data infrastructure, the pipelines that seed everything.
Crucial role. They need clear data requirements from you, what format, what frequency, what quality, and they need your code to be easily integratable with their pipelines. And you, well, you're completely dependent on them for robust, scalable pipelines that deliver clean, reliable, low-latency data. It's a constant handshake, a symbiotic relationship.
What about domain experts, the people who really understand the business area, healthcare, finance, logistics, whatever it is?
Oh, invaluable. They need explainable outputs and maybe visualizations from you so they can understand how the model is arriving at its conclusions and validate if it makes sense in the real world. And you desperately need their context. Why does the data look weird here? Is this feature actually relevant? Is the model's output practically useful or just technically correct? They're your reality check.
Okay, and the software engineer, maybe the app dev team, they're the ones who actually integrate your deployed model into the user-facing application.
Precisely. So they'll need a stable, well-documented API from your model service. They need clear expectations around latency and throughput, and you need their requirements for that API contract. You also need to understand the user workflow deeply to make sure the model fits in seamlessly and doesn't disrupt the user experience.
Which leads nicely to the UX designer, making that AI output actually user-friendly and understandable.
Yeah, they need to understand things like model confidence scores, how certain is the model, so they can design interfaces that handle uncertainty gracefully. And you need their designs to help manage user expectations, especially when the model isn't 100% certain, and present the information in a non-disruptive way.
And finally, a role that's becoming increasingly critical, the legal and ethics advisor. Compliance, risk mitigation, huge for AI now.
Absolutely non-negotiable in many areas. They need transparency from you regarding the data used, the model's decision-making process, evidence of bias and fairness audits, and clear documentation. And you need their clear guidelines on permitted data usage, definitions of fairness relevant to the context, and requirements for explainability. It truly is a full ecosystem, isn't it? Every role relying heavily on the others.
It really is. So to make all this collaboration actually work smoothly, you need a solid playbook, some ground rules. First, our sources stress establishing a common lexicon. Agreeing upfront on what terms like active user or churn precisely mean sounds simple, but
Oh, it avoids so many misunderstandings down the line. Misaligned definitions can totally derail projects months later when people realize they've been talking about different things.
and crucially, translating technical concepts into plain business language. Don't just throw around terms like overfitting.
Right. Instead of saying the model is overfitting, explain the business implications. Say something like, look, the model has learned the training data a bit too well, almost like it memorized the answers for a test. So the risk is it won't perform accurately on new, unseen customers. It might make bad recommendations or predictions out in the real world if we deploy it like this. That simple shift makes a world of difference in building understanding and trust.
Managing expectations with transparency is also vital, isn't it? AI isn't magic, despite the hype sometimes.
Exactly. Be really clear and honest about what the model can realistically achieve and what its limitations are. This builds trust and avoids the kind of disappointment and backlash we saw with projects like IBM's Watson, where maybe the marketing claims ran way ahead of the actual technological capabilities at the time. It reminds me of that time I tried to bake a cake using a recipe I thought was for cake, but it turned out to be for bread, technically perfect ingredients, maybe, but completely the wrong outcome because I had the wrong expectation for the whole process.
That's a perfect analogy. And finally, embracing iteration and feedback. Fostering a culture where it's genuinely safe to share ideas, even half-baked ones, and importantly, to report failures or unexpected results without fear.
Yeah, things like daily stand-ups, regular retrospectives, they aren't just meetings for the sake of meetings. They're essential mechanisms for tactical alignment, for course correction, and for continuous improvement. It allows the whole team to learn and adapt much more quickly.
Okay, fantastic. Now let's dive into the real nitty-gritty. The production-level project lifecycle itself. Our guiding philosophy here, as mentioned in the sources, often draws from CRISP-DM, that's the cross-industry standard process for data mining, but significantly augmented by the modern rigor and practices of MLOps.
Right. Think of Chris DM as giving us the main phases.
Yeah.
It lays out about 6 cyclical phases, starting with business understanding, then data understanding, data preparation, modeling, evaluation, and finally deployment. And it's deliberately cyclical, meaning you can always loop back to earlier phases to refine things based on what you learn later. MLOps, on the other hand, provides the how. It's about applying established DevOps principles, automation, versioning, testing, monitoring specifically to the ML lifecycle to make it repeatable, reliable, and scalable.
So let's walk through these phases, integrating the MLOps perspective. In phases 1 and 2, business and data understanding, you're defining those SMART goals: specific, measurable, achievable, relevant, time-bound, assessing data availability and constraints, doing initial exploratory data analysis, EDA, and crucially, verifying data quality, completeness, correctness, missing values.
And MLOps integrates right here. Think automated data profiling tools that generate reports, automated data quality checks integrated into pipelines, and proper documentation of data sources and lineage. It formalizes that understanding. The big pitfall to avoid here, the absolute classic, is garbage in, garbage out, or GIGO. You have to remember that no amount of sophisticated modeling downstream can compensate for fundamentally poor, biased, or irrelevant data upstream. It's foundational. Get this wrong and everything else suffers.
Couldn't agree more. Then we hit phase 3, data preparation. This is often where the bulk of the time goes in many real-world projects, right?
Oh, easily. It involves data cleaning, handling missing values through imputation, correcting errors, removing duplicates. It involves data integration, maybe pulling data from multiple sources. And then there's feature engineering. This is often a highly creative step where you derive new informative features from the raw data, like expanding date components, aggregating user events over time windows, calculating ratios. And finally, data transformation, like encoding categorical variables or scaling numerical features. MLOps is crucial here for ensuring consistency and reproducibility. Think data and feature versioning using tools like DVC, data version control alongside Git, and building reusable data processing pipelines, maybe using Apache Spark for large data sets so the process is identical every time.
Moving on to phase 4, modeling. This is where you actually select your algorithms, maybe try out a few different ones. You design your test strategy, how you split data into training, validation, and test sets. And then you train and tune your models, often involving hyperparameter optimization.
And MLOps brings in critical tools here, especially experiment tracking platforms like MLflow or Neptune.ai. These log every single training, run the code version used, the data version, the specific hyperparameters, the resulting evaluation metrics. This creates an invaluable, auditable, reproducible history of all your experiments. It's fantastic for comparing models, debugging issues, and tracking progress over time. And of course, writing clean, modular, well-documented code following standards like PEP8 is vital.
Phase 5, evaluation. This is where you rigorously assess how well your trained model actually performs. You measure its performance on that held-out test set using your chosen model metrics.
But it's not just about the metrics. You also need to assess alignment with the original business goals, perhaps through offline simulations or analysis. And critically, conducting a bias and fairness audit across different important user segments is becoming standard. MLOps integrates this through automated model validation steps in your CI/CD pipelines. Maybe a model only progresses if it passes certain performance thresholds and bias checks. A crucial pitfall here, though, is the accuracy trap.
Ah, yes, explain that one.
Well, imagine you have a highly imbalanced data set, like for fraud detection, where maybe only 0.1% of transactions are fraudulent. A model that simply predicts not fraud for every single transaction would be 99.9% accurate.
Right. Technically high accuracy, but completely useless.
Exactly. It catches no fraud. So relying solely on accuracy can be incredibly misleading in such cases. You need to look at more nuanced metrics like precision, recall, F1 score, or AUC/ROC to get a true picture of the model's effectiveness, especially for the minority class you care about.
Makes sense. Then comes phase 6, deployment. This is where you take your validated, approved model and actually put it into production so it can start delivering value. This might involve integrating it as a real-time API, setting it up for batch processing, or even embedding it directly into an application.
And the focus here shifts heavily towards operational concerns: scalability, reliability, latency, throughput. MLOps is absolutely central in this phase. We're talking full CI/CD for ML continuous integration, continuous delivery using tools like Jenkins, GitLab CI, or cloud-native solutions. We're talking about containerization using Docker to package the model and its dependencies for consistent environments across development, testing, and production. And often orchestrations using platforms like Kubernetes to manage deployment, scaling, and ensure high availability and fault tolerance.
And finally, the phase that's maybe not explicitly in the original CRISP-VM, but is absolutely critical for sustained value in the MLOps world. Phase 7, monitoring and maintenance. Deployment isn't the end of the story, is it?
Not at all.
Yeah.
It's really just the beginning of the model's life in production. You need continuous vigilant monitoring for several things. First, data drift and concept drift.
Okay, can you clarify the difference there?
Sure. Data drift is when the statistical properties of the input data the model sees in production start to change compared to the data it was trained on. Maybe your customer demographics shift or user behavior patterns evolve. Concept drift is more subtle. It's when the relationship between the input features and the target variable itself changes over time. For example, what used to be a strong predictor of customer churn might become less relevant due to market changes or new competitor actions. Both of these drifts are critical leading indicators that your model's performance is likely degrading or about to degrade.
Got it. So you monitor for drift. What else?
You also need to monitor the model's predictive performance directly, tracking those key metrics against predefined acceptable thresholds. And you monitor operational metrics too. System health stuff like latency, requests per second, QPS, CPU, and memory usage. MLOps involves setting up automated monitoring and alerting systems for all of these, so you get notified proactively if drift is detected, if performance drops, or if the system is struggling.
And how does this monitoring loop back? That sounds crucial.
Exactly. This monitoring shouldn't just produce dashboards, it should create a feedback loop. When significant drift or performance degradation is detected, it should trigger actions, maybe automatically retraining the model with fresh data, maybe flagging it for reevaluation by the team, maybe even triggering a rollback to a previous version. This feedback loop is what enables you to build self-healing, adaptive systems that remain relevant and effective over time, rather than models that silently decay after deployment.
Okay, this life cycle is comprehensive. Let's try and make it even more concrete with an end-to-end project deep dive. How about building a production-grade recommendation engine? That feels like a perfect microcosm of the entire process we just outlined, touching on pretty much every phase.
It really is. Recommendation systems are ubiquitous, and the business goal is usually very clear. Increase user engagement, drive sales, improve retention. Companies like Amazon, for instance, famously attribute a huge chunk of their sales, maybe as much as 35%, directly to their recommendation systems. The ML problem itself is typically to predict which items a user is most likely to interact with positively, often framed as a ranking problem. Show the top N items.
And the data needed for this is quite rich, usually falling into a few categories, right? You've got interaction data that could be explicit feedback like star ratings, or more commonly implicit signals like clicks, watch time, add to carts, purchases.
Then you have item data, metadata about the items themselves, like a movie's genre, cast, director, or a product's brand, category, description. And user data, maybe demographics, stated preferences, past interaction history. The Movie Lens dataset is a classic public example people often start with to explore these kinds of problems.
Okay, so for data prep and modeling, phases 3 and 4, you'd likely start with tools like pandas and Python for loading, merging different data sources, cleaning missing or inconsistent data, and doing some initial exploratory analysis. Pandas data frames are just so intuitive for that kind of tabular data wrangling.
Definitely. Then for a baseline model, a very common starting point is collaborative filtering, specifically using matrix factorization. The idea here is to leverage the wisdom of the crowd. You take this large, sparse matrix of user-item interactions and decompose it into smaller, dense matrices representing latent factors or features for users and items. Python's surprise library, often using algorithms like SVD, singular value decomposition, is great for implementing this relatively easily and finding those hidden patterns in user preferences based on what similar users liked.
But pure collaborative filtering has that well-known cold start problem, doesn't it?
Yeah,
It struggles with new users or new items because there isn't enough interaction data yet.
exactly. If you don't know anything about a user or an item, the model can't really make good recommendations. That's where building a hybrid approach often comes in as the next iteration. You combine the strengths of collaborative filtering, leveraging user behavior, with content-based filtering, which recommends items based on their attributes being similar to items the user liked in the past. This can be done in various ways, maybe a simple weighted combination of scores from both models, or you could get more sophisticated. For example, you could use the latent factors learned from matrix factorization as additional features fed into another model, perhaps a gradient-boosted decision tree, GBDT model, similar to how Airbnb experiences approach the recommendation system. It's about bringing different sources of information together to get a better result, especially for cold start scenarios.
Right, combining methods. So how do you evaluate if these models are actually any good? Holistic evaluation, phase 5 for recommendations, seems like it needs multiple angles.
It absolutely does. Offline, before you deploy anything, you use historical data. For prediction accuracy, if you were predicting ratings, you might use metrics like RMSE, root mean squared error, or MAE, mean absolute error. More commonly for recommendations, though, you're dealing with ranked lists, so you use ranking accuracy metrics like precision at K, what fraction of the top K recommendations were relevant, recall at K, what fraction of all relevant items appeared in the top K, or NDCG, normalized discounted cumulative gain, which also considers the position of relevant items in the list.
But those offline metrics, while useful for development, don't always perfectly predict real-world performance, do they?
That's the key limitation. They don't capture the full picture of user interaction or business impact. The true gold standard for evaluation is online A/B testing. Here, you randomly assign users into different groups. One group, the control, gets the existing recommendation system, while another group, the treatment, gets your new model. Then you measure the actual difference in key business KPIs over a period, things like click-through rate, CTR, conversion rates, average session duration, maybe overall revenue lift. This is really the only reliable way to know if your new model truly delivers better business value than the old one.
Makes complete sense. Finally, deployment architecture and monitoring, phases 6 and 7. What does a production recommendation system often look like?
Well, drawing inspiration from systems like Netflix's, you often see a multi-stage architecture designed for both relevance and low latency. First, a candidate generation stage. This quickly filters down the millions of possible items to a few hundred potentially relevant candidates for a given user, maybe using simpler models or rules. Then a scoring and ranking stage, where more complex, computationally intensive models like deep learning networks or the hybrid model we discussed score and rank these candidates precisely. And finally, sometimes a re-ranking or filtering stage, where you might apply additional business logic, diversity rules, or personalization tweaks before showing the final list to the user.
And the infrastructure behind that.
You typically have a mix. Offline systems, often using tools like Apache Spark for batch processing large datasets, training models, pre-computing features, or candidates. Online systems designed for low latency serving. This usually involves a fast key value store or a dedicated feature store to retrieve user and item features quickly, and the model itself deployed as a microservice. And often data streaming platforms like Kafka to ingest real-time user interactions, clicks, views, which can then feed into near real-time updates or future model training.
And what about monitoring specifically for recommendation systems? Any unique challenges?
Yes, besides the usual drift and performance monitoring, you need to be very watchful for unintended feedback loops. A common one is the popularity bias loop. Popular items get recommended more, so they get more interactions, which makes them appear even more popular, further boosting their recommendations. This can starve newer or niche items of exposure. So you absolutely need to monitor metrics related to recommendation diversity and the exposure rate of new or less popular items to ensure the system remains healthy and discovers fresh content for users.
Okay, wow, that really brings the whole life cycle to life. Now, this is where the possibilities really start to expand for those looking to push the boundaries. Leveling up with reinforcement learning. If classification and regression are mostly about making static predictions based on historical patterns, what about problems where the AI needs to make a sequence of decisions in a constantly changing environment, where each action influences future outcomes and the rewards might be delayed? That's the sweet spot for RL, isn't it?
Exactly. Think about playing chess or Go. A single move isn't judged immediately. Its value depends on how it sets you up for the rest of the game. That's the core idea. Learning optimal strategies over time through interaction and feedback.
So let's look at a fantastic real-world case study, real-time ad bidding, RTB, in online advertising. What's the business problem there?
The business problem is essentially an advertiser trying to maximize conversions, like clicks or purchases, while staying within a fixed budget. They have to bid in auctions that happen in milliseconds for the chance to show their ad on a web page or app. Now, traditional supervised learning can help here. It can predict the probability that a user will click on an ad if shown, predicting PCTR, predicted click-through rate.
Right, seems useful. But why isn't that enough?
Because simply predicting the click probability doesn't tell you what to bid. It doesn't account for your remaining budget, it doesn't consider what your competitors might be bidding, and it doesn't model the immediate impact of your bid amount on whether you win the auction and at what price. It misses the core strategic question. What is the optimal bid price right now?
Ah, okay. So it's not just about predicting likelihood, but strategically deciding the action the bid to maximize long-term return within constraints.
That definitely sounds like an RL problem. How would you formulate that? You typically frame it as a Markov decision process, MDP. You have an agent, which is your bidding algorithm. The environment is the dynamic ad exchange, including competitors and the users visiting the sites. The state S captures the current situation, things like your remaining budget, the time of day, characteristics of the user segment being targeted, maybe the historical CTR of the specific ad slot. It's all the information relevant to making a good bid. The action A is the bid price your agent chooses to submit for that auction. And the reward signal is absolutely critical to design well. It needs to balance the value of a positive outcome, like a click or conversion, with the cost of the bid. A common formulation might be something like value of click did click, cost of bid. This incentivizes the agent to bid smartly high enough to win valuable impressions, but not overspending wastefully.
That makes sense. But training an RL agent, I imagine the biggest implementation challenge in RTB is that you can't just let a learning agent loose with real money from day one, right? It would probably make terrible bids initially.
Exactly. Training with real money is far too risky and expensive. So, simulation is key. You absolutely need to build high-fidelity simulators. These simulators are typically built using vast amounts of historical auction log data. They aim to realistically model the behavior of competitors in the auction and the probability of users clicking based on different factors. This allows your RL agent to interact millions, even billions of times in this simulated environment, learning an optimal bidding policy through trial and error without any real-world financial consequences. It's like having a digital sandbox to practice in safely.
And given the huge number of possible states in RTB budget remaining as continuous, user segments are numerous, etc., you probably can't use simple methods like queue tables, can you? No way. The state space is enormous and often continuous. That's where deep learning comes in. You move from simple tabular queue learning to using deep queue networks, DQN, or similar deep RL algorithms. Instead of a giant table mapping states to action values, you use a deep neural network to approximate the queue function. The network takes the current state representation as input and outputs the estimated queue value, the expected future reward, for each possible bid action. This allows the agent to generalize its learning to new, unseen state combinations, which is absolutely crucial in such dynamic and complex environments.
Fascinating. And beyond ad bidding, where else is RL showing significant promise or impact?
Oh, quite a few areas. Dynamic pricing is a big one. Think ride-sharing services like Uber adjusting prices based on real-time demand and supply, or e-commerce platforms like Amazon dynamically pricing products. Supply chain and inventory optimization is another major area. RL systems can learn optimal policies for ordering, stocking, and routing goods across complex networks to minimize costs, reduce waste, and prevent stockouts, adapting to changing conditions. And perhaps one of the most impressive published examples was Google using deep RL to manage the cooling systems in their data centers. The RL agent learned complex, non-intuitive strategies for operating pumps, chillers, and fans that significantly reduced energy consumption, reportedly by around 40% for cooling. That's a massive real-world impact on efficiency and sustainability, directly driven by RL finding better control policies than humans could devise.
Incredible potential. So pulling all this together, how do you, our listener, cultivate this complete AI skill set? How do you become that bilingual professional we've been talking about, fluent in both tech and business value? The sources consistently point towards becoming what's often called a T-shaped AI professional. What does that mean exactly?
It means having deep, production-level expertise in one or two core areas, typically ML algorithms and robust software engineering practices, the vertical bar, the T. But critically, it also means having a broad understanding across the entire ecosystem, the horizontal bar of the T. This includes the data landscape, the specific business context you're working in, and how to effectively collaborate with all those different cross-functional roles we discussed. Depth and breadth.
Okay, let's quickly highlight the kind of progression you might see across key skill categories, moving from maybe foundational knowledge towards being truly production ready. For programming and software engineering, you evolve from maybe writing functional Python scripts for analysis to designing genuinely scalable, maintainable systems, mastering APIs, understanding system design patterns, getting comfortable with containerization like Docker. It's moving from scripting to engineering.
Yeah, and in data and databases, it's progressing from basic SQL queries to designing efficient database schemas, knowing how to leverage large-scale data processing frameworks like Apache Spark when needed, and understanding the nuances of building reliable ETL or ELT pipelines. For foundational machine learning, it's going beyond just knowing how to call functions in libraries like scikit-learn. It's truly understanding the underlying math and assumptions, being able to critically choose the right evaluation metrics for the problem, and diagnosing common issues like the bias-variance trade-off.
Right. And for advanced ML and deep learning, you might progress from just a conceptual understanding to being able to design, implement, and debug complex neural network architectures like CNNs for images or RNNSSL STMs transformers for sequences, mastering techniques for hyperparameter tuning, regularization to prevent overfitting, and grasping the fundamental concepts behind reinforcement learning if you go that route.
Then there's MLOps and cloud platforms. This is a huge leap from maybe just using cloud storage like S3 or GCS to designing and implementing full CI/CD/CT pipelines, continuous integration, continuous delivery, and crucially, continuous training using tools like Jenkins, GitLab CI, Docker, Kubernetes. It's about managing the entire life cycle of models in production, including that vital drift monitoring and automated retraining.
And finally, the top of the T, maybe the hardest part for many technical folks, business acumen and communication. This progresses from simply understanding that there is a business problem to being adept at translating those vague business goals we talked about into clearly framed, solvable ML problems. It's about developing the ability to explain complex technical concepts clearly to non-expert stakeholders and, perhaps most importantly, being able to directly connect your model's performance metrics back to tangible business KPIs they care about. This is where that magic of bilingualism truly happens, bridging the gap.
Absolutely. So how do you actually learn all this? For a curated learning path, start with foundational theory in math. Excellent books like the 100-page Machine Learning book by Andrei Burkhoff, or the classic Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow by Aurélien Géron provide great starting points. Supplement these with high-quality online courses. Andrew Ng's original machine learning course and his deep learning specialization on Coursera are still fantastic for building that solid theoretical grounding.
Then, for practical skills and projects, Kaggle is just invaluable. Don't just do their introductory microcourses, jump into the competitions. But here's the key. Don't just focus on trying to win the leaderboard. Spend time studying the notebooks and solutions shared by top competitors. It's an incredible resource, not just for coding techniques, but to see how they approach the problem, how they do feature engineering, how they validate their models. It's like looking over the shoulder of experts. And crucially, build your own end-to-end projects. Take something like the recommendation engine we discussed, build it out, maybe write a blog post about it, put the code on GitHub. A portfolio of tangible working projects speaks volumes.
Totally agree. Then for advanced and production level skills, you'll likely need more specialized resources. Look for dedicated MLOps courses or specializations on platforms like Coursera, Google Cloud Skills Boost, or AWS Skill Builder that dive deep into CI/CD for ML, deployment strategies on cloud platforms, and monitoring tools. For reinforcement learning, the foundational textbook by Sutton and Bartow is the Bible, but definitely supplement it with practical tutorials and maybe libraries like OpenAI Gym or Stable Baselines 3 to actually get your hands dirty implementing algorithms.
And finally, don't underestimate the immense power of community. Learning in public, engaging with others.
Oh, it's huge. Engage with Kaggle's discussion forums. Ask questions, share insights, follow relevant subreddits like R Machine Learning for research papers and discussions, and rLearn Machine Learning or Data Science for more practical questions and community support. And consider joining real-time communities on platforms like Slack or Discord. Data Talks Club is a great example, offering channels for quick help, organizing events, and providing fantastic networking opportunities. These communities are vital for staying current, getting unstuck, and continuous learning in this fast-moving field.
So, we've explored this journey, haven't we? The journey of becoming a truly impactful AI professional, someone who speaks not just the technical language of code and algorithms, but also the strategic grammar of business value.
Yeah, and it's this transformation, this ability to bridge the gap that allows you to move beyond simply building cool algorithms to actually solving meaningful real-world problems and delivering tangible results.
That's right. Mastering this dual fluency makes you the critical component, the linchpin, connecting AI's immense potential to measurable business outcomes. You become the translator, the collaborator, the bridge builder, and the engineer all rolled into one.
So with this complete blueprint for cultivating that T-shaped AI profile, the challenge we want to leave you with, our listener, is this.
What new frontiers in problem solving will you now explore? And what kind of truly impactful, value-driven AI systems will you be empowered to create now that you're equipped or working toward being equipped to speak both of these crucial languages?